this week, one of the exciting topics, I think, of my life. Most of my life, there were no planets except for the 9 that we know. We assumed there were planets around other stars. I assumed it. Astronomers assumed it. Most people thought there probably were. Some of my friends who believe in aliens knew that there were. But we hadn't seen them. We hadn't seen evidence of them. And just a few years ago, one of the most exciting things in my life happened. We heard the first news, and I'm guessing that you all remember this as well as I do, that the first new planets had been discovered around other stars. Or the first planets had been discovered around other stars, not necessarily new planets, new to us. Very exciting. And Dr. Wesley Traub is here tonight to talk to us about that, and we're very pleased to welcome him because of his distinguished career in this area. And let me tell you a little bit about Dr. Traub. He is a senior physicist at the Harvard-Smithsonian Center for Astrophysics. He's had a varied career in measuring chemical conditions from our own stratosphere out all the way out to detecting planets around other stars. Wesley Traub received his doctorate in physics from the University of Wisconsin in Madison, where he built an interferometer to measure lithium content on the sun. Wes Traub then moved on to record atmospheric conditions on Venus, Jupiter, and Mars, and then to concentrating on Earth's own stratosphere. In the 1990s, Dr. Traub turned his interferometry skills toward the dust clouds around young stellar objects, and recently combined his earlier interests in planets and atmospheric conditions to looking at the topic of extrasolar planets. Searching for and finding these other worlds are the first steps toward looking for life outside our solar system. It's a very exciting topic, and please welcome Dr. Wes Traub.
Sorry, I should have put this on before. Okay, thank you very much for that introduction. Yes, indeed, what I would like to talk about is the search for new Earths. That is assuming that there are Earths out there. So a lot of what I will talk about is conjectural and is mostly concentrating on how we would look for these Earths and what we would see if we actually were able to find them. And by Earths, I mean planets of our size. We know that there are Jupiter-sized planets out there, and we're really interested in the smaller planets in this talk. So what I want to talk about is, first of all, can we find other Earths? I mean, how would we go about doing it? So I'll talk about the telescopes and interferometers that we might use to do that. And then we are interested in what they are like. We don't just want to know that they're sitting there. We want to be able to characterize them, and so I'll talk about spectroscopy and colors to see what we can learn about them from both of those things. And then that leads to the question that many people are interested in is life present? And it is possible. I will show that there are some signs that you can use in the spectra and in the colors to determine whether life is probably present on the planet. And, of course, we're all interested in knowing when we can start looking. So that's the outline of the talk. There's a whole variety of ways that you can search for planets, and many of you know about these, but let me go through them because there's a huge list, and it always surprises me. The first one, in the way that planets were actually discovered a few years ago, is through radial velocity variations. This doesn't mean the radial velocity of the planet itself. It means, of course, the radial velocity of the star. If you have a star and a planet going around it, there's a center of gravity that they have to rotate around, and so the star will go back and forth as the planet goes around, and you can see the Doppler shift in the star itself. My only demonstration today is Doppler shift. You can get one of these for your car, and you can get the Doppler shift measurement. It's a radar scanner. It's what the police use to figure out how fast your car is going. You look at light waves and see whether they're shifted in wavelength, and that tells you how fast the star is moving, and therefore how fast you can figure out how fast the planet is moving. Astrometry is another technique. That means you're going to meter the astro. You're going to measure the angle of the star with respect to other stars. And of course, if a planet is going around a star, not only will it move back and forth along your line of sight, but it will move sideways as the planet goes around. And so if you have a very precise astrometry system, something that measures the angles between stars, then you can determine if there's a planet going around. This technique, just for reference, the technique requires being able to, if you want to see an Earth around a nearby star, it requires being able to measure about 1 micro arc second. And an arc second is a very small number, and a micro arc second is an infinitely small number. Nevertheless, there is an astronomy payload that's going to go up in a couple of years that's being built right now called SIM, the Space Interferometer mission, that hopes to be able to measure down to that level. So certainly that mission, if it succeeds, will be able to measure Jupiter's, but possibly if it just sits there and works for a long time, it may be able to measure Earth's. You can measure transits, the planet going in front of the star. I'll show a picture of that in a few minutes. I include pulsar timing here because that was how the first objects around stars were found that are of planetary mass. The pulsar was changing its pulsation rate a little bit. The time when the radio frequency pulsations were arriving changed a little bit, and I think 3 planets now are known, or planet-like things are known around pulsars. Gravitational lensing, you can see if a star is lensing an object far behind it, and you look at the increase in light as the gravitational field of the star concentrates the light towards us just for a few days. If there's a planet there, it will concentrate a little bit of the light on the side, and so you'll get a little blip in addition to the overall increase in brightness of the star. You'll see a little increase in brightness due to the planet. Disk shaping is a technique. If you have a disk around a star, a dust disk where the star is being formed, if there was a big planet around that in that disk, and it was going in a different, if it was in an orbit inclined to the disk, most easily visualized, then it would warp the disk or change its characteristic, and so you could indirectly measure. Visible infrared shift is a technique that is going to be used at the Keck interferometers and the VLTI, the European interferometers in Chile, to look at the center of gravity of the light from a star and a planet. If you remember, a star has white visual light, and the planet is usually emitting in the infrared. So the center of gravity of this system will be different if you're measuring in the visual, or it'll be a little offset if you're measuring in the infrared. And so you can use these 2 different wavelengths to see if the center of gravity or the center of fringes in an interferometer is shifted. You can actually look at the reflected light from a planet, which seems a little strange, but if the star is there and the light is reflecting off of it, it will make the whole system look a little bit brighter. Transmitted light is the same as a transit here, but with light going through the atmosphere of the star. And there are a couple of other things that have been mentioned before I get to the ones that I really care about here. Auroral emission, people have said, well, we have a really nice aurora going at the North Pole and the South Pole. Why can't you see that? It's got nice H-alpha line, and it should be very distinguishable from background things. It's probably very weak. Anthropogenic transmission, we don't call this man-made anymore. Anthropogenic means, radio signals, television signals that are going out that are being, oh my gosh. Wow, okay. All right, so now the 2 things that I want to talk about, if I get off of this slide, is coronagraphic imaging and interferometric imaging. These are different from all of the ones above in that what we try to do here is to isolate the light from the planet from that of the star so that you can actually say, okay, here's the light from the star, here's the light from the planet, I'm going to ignore the star and I can focus on the planet. And then you can start to look at you can tell from the light from the planet in ways that I'll talk about for the rest of the talk what its atmospheric composition is, and you can guess what its mass and its radius and atmosphere look like. And both of these techniques, coronagraphic imaging. Coronagraph refers to the fact that a corona, long ago when people were looking at the sun and they wanted to look at the corona, they would block out the sun and just look at this bright corona around the outside. So any telescope that blocks out the bright central star and lets you look at something faint around it is called a coronagraph. And interferometric imaging is the idea of building an interferometer, which I'll show some pictures of, with several telescopes, and you bring the beams of light together and you interfere them, and you can make the star disappear at the center and only have the planet shining through. So these are all interesting, attractive techniques. And I'll talk about these last two for the rest of the talk. Okay, so I needed some active things for this talk, so this is one of them. This is occultation, just to illustrate a few of those points. This is a NASA-made graph that shows the star and a planet going in front of it. This actually is the actual geometry of the actual only one occultation that we know about. And what disappeared there was, okay, I don't want to bring it back. What was being shown there was the intensity of light and of the whole star, and then as the planet went in front of it, a little bit of the star got blocked. And so the intensity of light dropped by, I actually forget what the number is, it's a fraction of a %, and then it got bright again. And this was a way of detecting exactly what was the size of the planet compared to the size of the star. And also light would shine. Let me try and bring it back. You can see when the planet goes across that there's a little fuzzy ring around it, and that's the atmosphere of the planet is trying to be shown here in this artist conception. And some of the light that transmits through that atmosphere will also cause a little dip at certain wavelengths that are characteristic of the stuff that's in the atmosphere. And so sodium has been seen in the upper atmosphere of this star, HD 147889, I think. Okay, this is a horrible graph, but I just wanted to say that there are Earth-like planets. What's plotted here is what the brightness of that planet would look like in magnitudes. And if you remember, a 6th magnitude star is about what you can see with the naked eye. These are 30th magnitude. And for different size planets at different distances, stars that are different distances from the sun, a few parsecs, the separation of the planet from the star is milliarc seconds. It's not microarc seconds. And this is what we're up against. We're trying to figure out at less than an arc second away from a star and maybe about 20 magnitudes or so dimmer than the star, is there a planet sitting there? So these are the kinds of data points that we want to discover. Okay, this is another cartoon, which is kind of interesting because wait, let me get it to start going. What we're showing here is an actual binary star system, Alpha Cen, and there are two stars here. One is plotted at the center, Alpha Cen A, and Alpha Cen B is the star going around it. But in this simulation, which was done to try and figure out how planets would look when you were actually looking at a real system, what we've done is to make the second star into a planet so that it's just reflecting the light from the first star. And you'll notice as it comes around, it's getting brighter. It used to be darker when it was up here, and it's going to get brighter and brighter as it comes around. And at about this point over here in this elliptical orbit, it will fade and disappear. So what you can tell, if you can think of this three-dimensional geometry, is that this planet is behind the star, and the star is shining light onto the planet, and we're looking at the reflected light. Oops, it's fading. It got black. Okay. It came above the plane of the orbit, so there's no light being reflected off of it anymore, and now you won't be able to see it in the visible, but it'll keep on going in its orbit. So this was one of a zillion simulations that we're making to try and see how easy it is to see one of these planets going around a star. But mostly it's fun to look at. That's all. Okay. So there are some, here are the two techniques that I was talking about, using an interferometer and using a coronagraph. This is the interferometer. Several years ago, NASA designed an interferometer that had, in this case, this is one of the multiple kinds of machines that could have been used, 4 free-floating large mirrors, maybe 6 feet in diameter or 10 feet in diameter, floating in space, very precisely arranged, and one place where all the light is going to be brought together. And the idea here was that light would come from the star into each one of these telescopes and be rattled around, I'll show you another slide, and combined in this central station. So you have free flyers, which is a lovely engineering problem here, and one combiner. The pattern of light that is detected on the sky from these 4 telescopes, if they're adjusted just right, looks something like this. What this means here is that if this is the star system that you're looking at with a bright star and some stuff around it, dust maybe, that the very center, you see this very center here is dark. That's what I was talking about before, about nulling out the star. If you adjust the paths of light from the star to the combiner here just right, you can make the star disappear in the center, and you can just see the dust or planets that are around it. And the actual signal that you get would look something like this in time if you rotate this whole array around a center. Here's maybe a better graph of that. This is a plan view showing the 4 telescopes and how the light from each one is bounced around to make the paths equal before it's combined in this central station. And here is a cartoon showing how the light from the star comes in as plane waves and is brought together as at a combining point. But if you add a phase shift here, which means that you just move that light beam half a wavelength back from where it would have been if it was perfectly combined, then the light from this beam and this beam will cancel out right on axis where the star is, and light from a planet on the side will not cancel out. And how to do this and how to make this nulling interferometer work is a lovely piece of optics, and it does work. It's been done in the laboratory, and it's a possible way of making an interferometer in space and searching for a planet. This is a slightly better. Here, if the Earth and Mercury was hiding in the center here of this system, and Mars and Jupiter were there, and you have this pattern superposed on top of that. In other words, this times this equals this output, where you just see the light from the dust on either side and maybe some glimpse of the planets. And as you rotate this whole system, you'll get light intensity versus time, which wiggles up and down due to each one of the planets coming and going, and then you can disentangle this whole thing. It looks like a mess, but it really would, in principle, it would work. So this interferometer has some advantages. You can see the whole star system at one time. You can see some biomarkers, molecules which will tell you about life, which I'll tell you about later. You can measure the planet's size. There are some disadvantages. There's a zodiacal light. The dust that's floating around the star will have a bad effect on this kind of interferometer. It does not measure oxygen or chlorophyll, which I'll talk about later in the visible. And free flyers are just complicated. Some of us think that they're complicated. There's an alternative that after that design was worked up by NASA, some of us were thinking about how to, well, we're actually in a government-sponsored competition to think about how to do this, and came up with the idea of trying to use an ordinary telescope, which at first blush seems really kind of crazy, but the more we thought about it, the more clever inventions developed that would make it possible. So this is a graph by Ball Aerospace, who was the partners that we were working with, showing how light would come from a star and be focused by an off-axis parabola to a focus up here, just outside the spacecraft somewhere. And by the way, this parabola here is something on the order of 8 meters or 25 feet in diameter and half that wide. So it's a very, very large piece of glass with no obscuration in the center. There's a secondary mirror which brings the actual image down to here, and then there's some rattling around in the back where the image is brought onto a detector. And with this system, basically it focuses all the starlight in back, but there are a couple of tricks that you can play to make the starlight go away. In a coronagraph, this is the basic optics of a coronagraph. You have a telescope, a lens, mirror, something like that. You focus your star at a point here. And after that, well, at this point you can put a little black dot to block out the star, but some of the light, and in principle then the light from a planet which is focused somewhere else will come around it. But there is a lot of diffraction from an ordinary blocker here, and you just can't block out enough of the star. And then the light can be re-imaged again back here, so the star and the planet would reappear back here. There's two things that you can do. One is that you can put a mask at this place that's carefully designed so that it really does knock out the star and allow the planet to come through. And another thing that you can do is you can put a special shape back here, not just a circular aperture, but a shape that I'll show you a picture of, which makes the star essentially disappear, makes the star isolated back here so that the planet can be seen right next to it and not be covered by diffraction fringes. The kind of mask that you can put on the pupil, the objective lens of the telescope, would, if the telescope had a circular shape like this and you cut out a piece of paper, in fact, this is a photograph of an actual experiment that was cut out of a piece of paper in the laboratory with these funny-looking shapes on it. Then it will, for those of you who know about diffraction, it will diffract the light from the star up and down in the directions perpendicular to these edges. And you'll notice that there aren't any diffracting edges pointing in this direction. Not too much, at least. It's all pointing off at a diagonal. And what happens is that the light from this star then, instead of forming a bright central image and having lots of area rings, which are really quite bright, a few percent and a few tenths of a percent and so on down, which is still much brighter than the planet. Instead of having these area rings around here, all of that diffracted light goes off in up and down directions, and you've got very dark spots left on the left and right where the light from a planet could come through. This is really kind of magical. Here's an actual laboratory experiment where they cut it out of a piece of paper and shined a laser on it. And you can see, in fact, all the light goes up and down. This is way overexposed. And there's a lot of dark space here where a planet could come through if there had been one in the target system. This shows the same thing again with several apertures and producing an even bigger dark space over here. This is another kind of system that I was talking about before. If at the focus where you would normally have a star focused in the first place, you put a mask, which is not just a blob of ink, which is the first thing you'd think of, but a mask that is formed out of a sinusoidal grating, sort of like the kind of thing that you get in the supermarket when you're checking out. That, if you carefully design that grating, and in fact this was designed by Mark Kushner, who's in the audience, then it will cause all the light from the star to really disappear in the center, which also seems kind of magical, but it really is true. And light that comes and is focused outside that mask at center at the edge, a planet, would all come through. And so this is another way of trying to get rid of all of the light from a star. Both of these cases can get rid of the huge amount of light, which is a factor of like a billion of the star, and allow the planet to shine through. This is another cartoon for our amusement. What this is a compact telescope. This is just to show how you might put a large telescope. You remember I said it was 8 meters in diameter. This is probably not the way you'd want to go because this telescope is made up out of segments, and the segments are here, hexagonal, and they're all stacked up. And if I let this cartoon, this animation run, you'll see that the unfolding in space puts the secondary up here, and then the segments, the hexagonal segments of the mirror come out, and they go around and they walk around. You can see the nice reflection off of the mirror here. And it'll fill in the 6 segments around the edge. And then when it's all done, the struts will go up and put the secondary mirror in the right place at the top. This is just to show that people are spending a lot of effort trying to think about how to put a big mirror in space. And I didn't say it, but one of the problems with putting a mirror in space is just simply that we don't have rockets that are big enough. The rocket fairings that you can get in the United States only allow you to put something in that's 4 meters across. And so if you want an 8-meter diameter telescope, either you break it up into little pieces and unfold it, or you make it long, 8 meters in one direction, and sort of stand it on edge and stick it in that rocket. Those are the 2 possible ways of doing this. So for visible coronagraphs, and typically these things are operating in the visible, whereas that interferometer that I showed was operating in the infrared. There's no real strong reason why they have to be that way, but there are reasons why it works better this way. There are advantages to it. You can get a snapshot of the entire solar system. You can see a bunch of biomarkers, things that tell you if there's life there. And you can infer properties of the planet, like its mass and its surface properties. There are some disadvantages. This 8-meter mirror is pretty big. But on the other hand, so the interferometer was probably 80 meters across. So both of them are very large. And basically, you require a very smooth wavefront, by which I mean the mirror has to be polished until the surface of the mirror is effectively about the size of half of an atom across. And normally, you can't polish a mirror that well, but if you re-image the mirror onto another piece of glass that you can deform and take out any little bumps that are on the primary mirror, this so-called deformable mirror then can compensate for the bumps that are left in the polishing process in the primary mirror. And you can produce an almost perfectly smooth mirror. Okay, so I don't have many graphs like this for those of you who don't like graphs, but there is a question. Are there any Earth-like planets out there? And so this is just my attempt at trying to figure out what the answer to that is. What I've plotted here is the planet mass in terms of masses of Jupiters. And so this zaggy line here is the actual number of planets as of about a year ago that were discovered. And they range, as you can see, between 1/10 of a Jupiter and 10 Jupiters in mass. It turns out that there's nothing up in this range here, which is another story. So the question is, are there any things down at this level here, which is about where an Earth would be? And what I'm showing here is that there's a natural cutoff in the experimental method, the radial velocity technique that was used to measure these planets here. There's a cutoff at 20 or 10 meters per second accuracy that pretty naturally explains this drop-off here. So there could be planets out here. And furthermore, the blue line is what you get if you plot up the number of things in the solar system and scale it so that it fits on this graph. It shows that there aren't any really large objects bigger than Jupiter, and then all of a sudden there's a bunch of smaller and then even smaller objects. So I take this as a suggestion that it's quite possible that other planetary systems have Earth-like things around them. It's worth our going out and looking for it. Okay, how bright are these things? This is a plot showing the intensity of light on this axis in orders of magnitude, not just magnitudes, versus wavelengths in microns, which got sort of covered up by my color here. And it goes from blue to red, and this is the visible part of the spectrum, this bump here. This is the light you see this is the sun. And this is reflected light off of the planet Earth. And you can see that the reflected light from the Earth, if you stood away a huge distance, like 10 parsecs to one of the nearer stars, there is something like 9 orders of magnitude between the peak of the sun and the peak of the Earth reflection, which means you've got to get rid of this 9 orders of magnitude with that coronagraph in order to be able to see an Earth. Well, sorry, that's a Jupiter, and an Earth is plotted in blue here, and Mars. In the infrared, these planets emit room temperature radiation. All planets do. Here's the Earth with a spectrum superposed. And here's Jupiter, a little colder and longer wavelengths. And you can see that there's a lot less distance between the star and here. There's only a factor of 1,000,000, which means that the interferometer, if it operates in this wavelength, has to get rid of a factor of 1,000,000. And a coronagraph, if it operates here, has to get rid of a factor of 1,000,000,000. This is really challenging, but it should be possible. And what's superposed on here is a spectrum, which I think we're going to get to next. A spectrum. Okay, I rather like spectra. They tell you all sorts of things. This is actually, Christine gave me this slide, so I don't know exactly where it came from, but it looks like the transmission of the Earth's atmosphere. So it goes blue, yellow, red, and then very red. And it shows things like the 7,600 angstrom band of oxygen. This is the oxygen A band, the Fraunhofer band, and these are water features. And you can see that the spectrum is falling off at the short wavelengths, which is due to the ozone layer overhead, cutting off, just absorbing radiation. And here it must be that the detector just stopped working. But you can tell lots of things from a spectrum. And I would claim that you can actually learn much more than people had thought. And I'm sorry, these don't show up very well. What I've shown here is the reflected light, the relative amount of reflected light. So it goes from 0 to 1. From each of 6, 7 objects in the solar system, Jupiter and Uranus. So just for example, these are the spectra that we just measured in the past year to see what was going on. The straight lines are photometric curves, which agree pretty much with the spectra. The whole idea here is to look at the outer planets that are gas giants and realize that their spectra have very strong absorption in the red part of the spectrum, both cases in the red part due to methane and ammonia in the case of Uranus. But methane and ammonia here, and I don't think there's any ammonia here. There's a lot of, these are all methane bands out there. You can clearly tell the difference between that kind of spectrum, if you just look at big blocks of this spectrum, and one like Venus, for example, which is perfectly smooth out there and has a high reflectivity. It's up around 70%. It falls off for some reason that I'm not sure about, some ultraviolet absorber in the ultraviolet, but it's very smooth. And then just for comparison, if you look at rocks, the Moon, Mercury, and to some extent this Mars spectrum is not very good, but rocks tend to reflect in the red, and they're very flat, and they don't have these absorption features or these fall-offs. On the other hand, Earth looks quite different than all of these. Earth is a flat, like 30% reflectivity. It has a big absorption feature due to the oxygen A band at 7,600 angstroms. All these features here are water vapor features. There's another oxygen feature. This is not noise. It's mostly real stuff in the spectrum. The spectrum goes up, and I've extended it with a theoretical line here in the ultraviolet to 3,000–4,000 angstroms. We didn't measure that far. This is the light that's scattered by Rayleigh scattering, just light that's scattered off of the molecules of air. This is the blue sky, basically. And this little bump here I'll show you later is the sign of chlorophyll. So the Earth really looks different from any other planet. I'm going to skip through these. Basically, this is just to back up my statement that if you can measure the flux from a planet, you can guess a lot about its density and its albedo, its mass, its radius, and its temperature, and to with respectable error bars, and measure the atmospheric pressure to like 25%. Okay. So to come to a spectrum, this is a calculation, that we've made of the reflected light from the Earth, theoretically, in the visible part of the spectrum, all of these, and for different molecules, and then in the infrared part of the spectrum. And the purpose of all of this was to try and start seeing where the best place to look would be, infrared or visible, and compare them. And I guess the bottom line I should just tell you right now is that both of them seem to be very interesting places, and in fact that's now NASA's official line, that they're both interesting. But there are some more interesting things in the visible, as I will tell you, that weren't in this report. Basically, this shows a spectrum from, as I said, from red to blue, which is backwards from the previous ones, of all the spectral lines. And then we've broken it up into pieces so that if you want to study this, you can do it. Water vapor has lots of bands out in the infrared. Infrared astronomers work in these transmission bands of J and H and K here. This is the visible part of the spectrum. This is the near infrared. Oxygen has this oxygen A band absorbing here. Ozone has absorption in the middle of the spectrum and in the ultraviolet, not shown. Methane and CO2 also absorb. And likewise in the infrared, there are huge absorption lines, particularly of ozone at 9 microns, CO2 at 15 microns. This is what causes basically most of the greenhouse effect on the Earth, ozone to some extent. Here's methane, and here's nitrous oxide. These are all useful things for telling if there's life on a planet. There's some other species that you might be interested in, like sulfur dioxide, SF6, clearly a man-made thing, freons, which we are not making anymore. But you would have to have huge amounts extra than we actually have on Earth right now in order to be seen in a spectrum of this quality. Here's a quick look at what the Earth would be like if it had life on it versus if there was no life. And you can also read this to say what Earth might have looked like before life would actually began on Earth. The actual abundances of molecules, of these four molecules, are such that oxygen increases by about a factor of 100 if there's life on Earth. It's just a round, and obviously in very round numbers. Nitrous oxide is produced by life hardly any other way, and so it increases a lot. Methane increases a lot, and CO2 goes way down. It's used by plants. So how can you tell whether there's life on a planet or not? Well, you'd like to look for nitrous oxide and methane lines. Unfortunately, they don't have very strong lines. They were in the spectra that I showed before of the infrared, but they're not very strong, and so they're a little hard to see, and they're also mixed up with water vapor, but it's potentially possible. Probably the key thing that's really most important is to look for oxygen, and this is sort of a consensus opinion of people, of mine and other people, that looking for large amounts of oxygen is really a key thing in looking for life, because there is no chemical way that people can think of producing large amounts of oxygen, whereas there are chemical means of producing methane, like from volcanoes, for example. And as you saw, methane was abundant in Jupiter, so it's not if you saw methane, you wouldn't know whether it was produced by life or it was produced by, if it was just there from primordial abundances. So, for example, ozone in the visible part of the spectrum, if you increase the abundance of ozone, it makes this big line stronger. Oxygen in the visible part of the spectrum, if you increase the abundances from 0, it makes no absorption and it gets much stronger. Nothing is interfering with these lines. That's one of the purposes of showing this graph. Okay, we did a check of this, which is kind of interesting, and actually people seem really interested in this, so I'm going to focus on it a little bit. We measured the actual light reflected from the Earth. Surprisingly, there are no spacecraft up there looking at the Earth trying to see what the reflected light looks like, because this is such a boring experiment that nobody's put up a spacecraft to do it. But there's lots of spacecraft looking at little tiny pieces, by the meter of the Earth, but not the whole Earth. So here we are. We're trying to look at the whole Earth. And how do you do it? Well, you can look at the light that's reflected off the backside of the moon. This is the dark, this is Earth shine. Light that has come from the sun to the Earth. This is my big exercise in PowerPoint here. Learning how to get light to the dark side of the moon, and then it reflects off and it goes down to a telescope, and this is Tucson. And this is actually the way the configuration of the Earth and the moon looked like a year ago, late June, when this experiment was done. Tucson was here, the sun had just set, the light was reflecting off the Pacific Ocean in East Asia and hitting the moon. And then you can also you can look at the light on the bright side and see what that is and divide these two by each other. And then you get the difference between them is the light that's reflected off the Earth. And we measured this spectrum here, which shows from, I didn't put the colors in here, sorry. This is red, this is blue, and this is red, okay? This is the spectrum that gets reflected. And as I showed before, this is increasing in the blue due to Rayleigh scattering from, here's a plot of Rayleigh scattering down here. Here's the oxygen line. This is oxygen all by itself. And here's water, oxygen. Here's this large feature, this big dip here is ozone in the middle of the spectrum. And then there's a very strong ozone band out here, which I didn't plot. And this was noise on the detector, which we tried to take out. The point is, if you add up all of these spectra that we adjusted, least squares fit, until they look like the experimental spectrum, it matches it pretty well. We had to add one little thing. This, not very well shown up green plot here, this shows an enhanced reflection from 7,000 angstroms outward and basically nothing at short wavelengths. And this is the reflection of plant leaves on land. And that is we think that is the origin of this bump. On the other hand, the bump doesn't continue out here, so we're not really sure about it. But it's very provocative. We think that we detected the reflectivity of chlorophyll on the Earth in this spectrum looking at the moon. And the whole purpose of doing this, of course, is just to show that you can do something remotely and see what the spectrum looks like. This plots up the details of the spectrum. This is the clear air all by itself, just to show that we've broken these things up. Rayleigh scattering from molecules does this 1 over lambda to the 4th. Scattering from ocean water has a different, and aerosols. All these signatures are different, and we can analyze the spectrum in terms of them. And it was a very simple model that we used of light being transmitted through the ozone layer in the stratosphere, through the troposphere, and then being reflected off of air or ocean or vegetation or just land. And we also put clouds in here, some clear space, some low-level clouds and high-level clouds, which are statistically sort of what you would expect for the Earth. And we adjusted these things. We also did a measurement of we did a calculation of the infrared spectrum, as I said before. This is the infrared spectrum from the radio red at very long wavelengths. This is 10 microns, and this is 20 microns. Oh, there it is, 10 microns, 20 microns. This is the 15-micron band of CO2. That's ozone. This is water vapor and methane and nitrous oxide, all in here. And the reason they don't equal a black body spectrum, which is the emission from the ground, is that these molecules are all absorbing. And these are water absorptions in the far infrared here. So this is a theoretical spectrum of the Earth, looking at it from the top, integrated over the whole Earth, and including, in this case, some clouds. and spectral lines. And we did a validation of that one too. This is I'm sorry, this doesn't show up very well. TESS is an experiment that was sent to Mars with a spectrometer on it in this spectral range. And a few days out into its orbit path to Mars, they turned it around, aimed it at the Earth, and recorded the spectrum just for fun. And the spectrum is this green thing, which we got out of the literature. And then we took our model and adjusted the amount of low clouds, because clouds change from day to day, and didn't adjust anything else, basically, and got the blue line, which matches it quite well. Not perfectly, but quite well. And so we consider that our calculation of what we were looking at is validated by this spacecraft experiment. So both parts of the spectrum have been validated by looking at something. Now, there's a lot of interesting variations on what the Earth would look like. I mean, the Earth didn't look like it does today, all the way back into history, of course. There was this time when, at the beginning of life, the Neoproterozoic time, 700 million years ago, when it is thought that the Earth was covered with ice, and then it got really warm, and then it was covered with ice again. And by covered by ice, I mean ice all the way down to the equator. Some people's ideas is that the Earth was totally covered with ice. The oceans, the land, there were glaciers all the way down to the equator. And what would have happened in a case like that is that, well, let's see. I don't want to go through this thing in great detail, but if the carbon dioxide in the air starts to get pulled out, then the greenhouse effect, which is keeping the Earth warm from freezing, there are volcanoes, and volcanoes belch because we have plate tectonics. Volcanoes are continually putting out a small amount of CO2. And so over a period of like 10 million years, the volcanoes can put enough CO2 into the air to cause a greenhouse effect to warm it back up again. And when that happens, the ice is going to break up and drop stones and whatever it does. And the warm oceans will then start to deposit, if they're covering a piece of land, the oceans will rise because the ice is melted, and it'll deposit carbonates. I mean, there's a lot of chemistry going on here, but it can deposit things on the land, and then the whole cycle can start all over again if a lot of the CO2 gets used up. This is not what people expected, but the evidence is there that it really did happen. This is the evidence. This is a picture of carbonate and glacial layers in Namibia, in Africa, pretty close to the equator of Africa. And what this person standing next to is a bunch of rocks that were dropped from glaciers, where the glacier had scraped along the ground, and then when it melted, it just dropped the rocks straight to the ocean floor. This is all very characteristic of glaciation. Then the stuff above it is a carbonate layer of deposits that only could have happened if it was at the bottom of a seafloor. So this then was covered with an ocean, and all these carbonates got deposited. And there are several layers like this. This whole thing alternates several times. And this is pretty good evidence that there really was an ice-covered Earth, and then it got hot. And so I'm just calling it hothouse and snowball. I'm only showing this because I was standing in New Mexico last week, and we saw on the mesas this white layer on the top. And the mesas were being held together by this white layer on the top. And here we drove up to it. And there's like a 3-foot layer of carbonates. You can just pick this stuff up and it crumbles in your fingers. It's like chalk. It is chalk. And here the rocks are falling down the hill on the side of the mesa. But this happens all over the world. But I just put it in there because it was fun. Okay. There is a different spectrum from each of those two cases. We've calculated what we think that the air and the reflection of the Earth would have looked like. And there's a difference between the snowball and the hothouse Earth. There's less ozone. There's less oxygen. There's less methane. A lot of these things are different. Anyhow, one should be able to tell the difference between those two kinds of states. It certainly would be interesting. And you can do the same thing in the infrared. It has different spectra, we think, in the infrared. There's another interesting thing that goes on the Earth, and that's methane hydrate. Methane can form, if methane bubbles up from the rocks underneath the ocean and gets to the bottom of the ocean, there's a condition where it can form into snowballs, basically. Even though it's not cold enough to make ice, it can form methane ice. And so methane and water form these rocky things, which are under a lot of the oceans. This is a view of the North Pole, Greenland, and this is a map of where methane has been plotted out up there. A a lot of the oceans are covered, have methane underneath them. And if all of that methane ever got triggered to boil off, which it could if the oceans got more shallow or if they warmed up, then you would have a huge amount of methane. It would act like a big greenhouse effect, and you would see it in the spectrum also. Just for those of you who like phase diagrams, this is a plot of where the methane can form deep in the ocean, rather shallow in the ocean. Here's the depth in kilometers. These plots go together. And this is the temperature of the ocean as you drop down and going, it gets colder and colder, and then when you hit the bottom of the ocean in this plot, it starts to get warmer as you go towards the center of the Earth. There's a region in here where methane and seawater can live together and where they can be together in the floor of the ocean. And so at a certain depth, below a certain depth, which is not very much, less than half a mile, the seafloor can have methane hydrate in big deposits on it. So this is a real thing, and usually we don't think much about this kind of topic. And the methane spectrum can also be calculated. Okay, so if you come back and think about what are the advantages or disadvantages of different parts of the spectrum, I've tried to summarize that here. The visible and the infrared. And the reason for going through this summary is because at some point, if you really want to find planets, somebody's going to have to break down and decide if we're going to build a visible coronagraph or an infrared interferometer, because we're talking about spending like $1 billion to do this, and so you want to think about this before you actually jump out and do it. So let's go through the list. Visible, you can see CO2 if there's a lot of it, but you can certainly see it in the infrared. You saw it in the spectrum there. Water vapor, you can see in both cases. That's nice because you need water for life, of course. Oxygen, there's a big band that I've shown several times in the visible. There is no such band in the infrared, which is a pity. Ozone has bands that you can see both in the visible, in the middle of the visible, and in the ultraviolet. And also there's a big band in the infrared. And they're both useful for detecting ozone. Ozone comes from oxygen. If you see ozone in large amounts, then large amounts means like what's in our stratosphere, then you know that there must have been maybe the amount of oxygen that we have underneath it, or it could be even down to 1% of that, because the ozone will form no matter how much oxygen is here, as long as it's above some certain threshold. So for even small amounts of oxygen, like in the early history of the Earth when oxygen was just being produced initially, you would get a fairly large ozone layer up on top, and you would be able to see that in the infrared very easily and also in the visible. Only later, when the oxygen builds up on Earth from animals, would you be able to see large amounts of it. The other argument about oxygen is that it is true that there is oxygen on places that we think do not have life, like Mars and Venus, a couple of moons of Jupiter, and we're pretty sure that there's no life there, at least not producing this oxygen. The amount that's there has been calculated to be consistent with amounts of oxygen that can be produced by just photolysis of water, ultraviolet light hitting water and breaking it apart, or even breaking apart CO2, but water is much easier. So photochemically, you can produce oxygen in small amounts, but when you produce large amounts, it begins to be eaten up by something else, like other hydrogen-type compounds, and it won't last very long. But to produce huge amounts of oxygen, you need a huge imbalance like we have on Earth. Plants producing lots of oxygen, people using it up, and it's completely out of equilibrium. There are some other molecules here that we have talked about. Methane, you can see if there's a lot of it in the visible, and you can see it also if there's a lot of it in the infrared. Methane is produced by cows, phytoplankton, other things that are alive, but it's also produced by volcanoes, and it's here before the Earth was formed in the first place. So to me, this doesn't have any great attraction. Nitrous oxide is something that's really nice because it's only produced by life, but we don't have any absorption bands in the excuse me, the visible. And in the infrared, that band, if you recall, was sort of stomped on by the methane and the water vapor at the same wavelength, so it's kind of difficult to see. It's possible to measure the temperature. You'd like to know what the temperature of a planet is. If you find that the temperature is somewhere in the range of liquid water, then you know that probably there can be life on the surface, at least life the way we think about it. And you can derive those numbers or look at the thermal emission and figure out what the temperature of the planet probably is. Although I should say here, the temperature, if you look at the Earth and measure its temperature, you would get a number way below freezing, because the temperature of the top of the, if you calculate what the temperature of the Earth is, it would be way below freezing, because that's the equilibrium point at which radiation can escape to space, and the temperature at that point up in the stratosphere, outside of an airplane, it's really cold, would indicate that there isn't any life. But we have this huge, as we've mentioned, greenhouse effect, which traps the heat, and so it's much warmer down here where we are. You can estimate what the pressure is from the visible spectrum, and I don't know quite of any way of doing it from the infrared. And you can guess about the size of the planet and the mass. I either skipped or I didn't. Somewhere that slide disappeared here, but I had a discussion of how you could estimate the mass of a planet and the radius. You care about the mass of a planet. I mean, what do you ask, why do I care whether the Earth is little or big? It makes a big difference if the planet is the Earth. Thank goodness. If the mass is like Earth size, then people believe that you can have plate tectonics. There's enough heat and circulation in the interior to move the plates around on the surface, and this is very good for life, I think, because it recirculates stuff. It doesn't lead to a static planet. If you're on Mars, maybe they had plate tectonics there for a little while, and even Venus, but it probably stopped, as I understand it from what people have guessed, and that means that the planet can stagnate, and you don't get recycling of carbon dioxide into the atmosphere and other materials. So it would be nice to have plate tectonics, so you'd like to know what the mass is. Also, if it's too massive, then you're ending up in the regime of Jupiter, where you capture all of these light gases, and they just stick around forever and ever, and the surface, whatever that is, of the planet never has a chance to have life on it, so you don't want the mass to be too large. So there's a nice range of mass here that you would like to find out about. And finally, this thing of chlorophyll, which shows up with this reflection spectrum in the visible and has no counterpart in the infrared. So if you're looking for plants, you would like to be able to see the chlorophyll. You say, how long would it take? I mean, suppose that you could build these instruments and they really work perfectly, and you are only limited by the rate at which you could collect photons and count photons, which is what this calculation is based on. If you look in the visible and you use a coronagraph and you have an 8-meter diameter mirror, which we don't have yet, but you might, then you could detect oxygen in a few days. You could detect ozone in a few days, and water, and probably not carbon dioxide. But you can detect these things by just sitting around for a period of time on the order of a few days, which is very encouraging. If you build an infrared interferometer of the type that NASA originally proposed, the kind that I showed before, as I said before, you can't see oxygen because there is none in the infrared, but you can do a pretty good job with looking for ozone in comparable amounts of time, less than a week. Ozone and water vapor, and there is a huge CO2 band there, so you have an advantage. You can see CO2. So there's a trade-off between these two parts of the spectrum, but they're both comparable. Roughly speaking, it's a few days to detect any one of these gases, and that's after you've detected the planet and known a lot about it in the first place. So, to conclude, I didn't show it, but there are hundreds of nearby stars that can be searched for Earth-like planets. There are actually about 250, because we've gone through the list of all the nearby stars and eliminated the ones that are binary stars or triple stars, eliminated the ones that are too young or too active to have had a planet around them, eliminated lots of stars. The ones that are left and that are not too far away, like less than 25 parsecs or so, form a list of at least 250, which is a nice sample to look at for any one of these instruments. It would make it worthwhile spending the money on it. As I've mentioned, both the visible and the infrared have merits, and so far we don't think of any other part of the spectrum, like the radio or something, X-rays, to look in. I mean, we have all thought about these other parts of the spectrum, but the visible and the infrared seem to be the dominant regions. In the visible, there's an advantage that you can measure oxygen. You can see Rayleigh scattering and get the atmospheric pressure, and you can see chlorophyll. In the infrared, there's an advantage that it's never dark. If you remember that cartoon of the planet going around, the simulation of a planet going around a star, it was dark most of the half of the time or 2/3 of the time because the light just wasn't shining on it. So that's an advantage of the infrared. Which one would go first? Excuse me. Well, the official, after we've done all of this study and reported back to NASA, the official conclusion is that we'll see which one of these kinds of instruments can be developed over the next few years, and that is the program of NASA in the United States and ESA in Europe to try and develop the interferometer and the coronagraph over the next 3 years to do the technology, to learn how to polish mirrors very smoothly, to learn how to make these masks work perfectly, all of that kind of stuff. So in 3 years, come back and somebody will give you a talk telling you which one of these guys won, and then presumably some building will start, and that should take a couple of years. And the NASA charts, which tell you how long it takes to fly a spacecraft, which are never true in the first place, say that you could fly this thing starting at about 2011. That's it. Thank you very much.
Thank you very much. Can you hear me? Can you? Yes, there we are. There I am. We would be happy to take some questions. Yes, right here.
On that moon experiment, I thought that people had done that quite a few years ago with the possibility of looking at the pollution effects in our atmosphere.
That's right. There was an experiment a few years ago, before we did this one, to look by Good et al., and they looked at the light reflected off the moon, and the idea was that you could, I think the idea was that you could tell something about, it was an Earth monitor. You could see the amount of cloudiness and so on. And so that was, people have been looking at the moon for a long time. I mean, but to look at it with this specific, I must tell you that when we first discussed doing this experiment, I thought it was kind of silly because I thought, well, we can calculate all these things and I know exactly what they should look like. But it turned out I was wrong because I had totally forgotten about Rayleigh scattering, which I think now is very important. And by looking at the spectrum, you can actually see the chlorophyll in it, which was a big surprise. I mean, chlorophyll is not an astrophysical molecule. That's not something that we have in our tables. And so, I just never thought of it. So there was a lot of virtue in actually doing the experiment. And you can be sure that we're continuing to do these experiments to try and see this stuff come and go also.
Can I just finish it up?
Sure.
Chlorophyll, you should be able also to see whether, I think dead plants have a different ratio of two wavelengths, of blue and red one. Whereas healthy plants with a rich amount of chlorophyll, that ratio is different. So you might be able to tell about the condition.
Probably. The question was, the comment was that dead plants and live plants have different reflectivities in this part of the spectrum, and I think that's basically true. I'm not a biologist, and I just look these things up that other people have done. But it is surprising, if you look at plant leaf reflection spectra, they are astoundingly similar for a whole range of different kinds of plants. Deciduous trees, evergreens, all sorts of things that grow on the ground. There's a very common factor here, but when they die, they probably turn a different color, yes.
Somebody right here.
You've got 4 8-meter telescopes down in Chile at Para now,
Mm-hmm.
And they're going to have an interferometer in
Yes.
4 or 5 years.
Yes.
Why can't
Well, they've actually interfered beams already, but
right,
yes.
the final
Right.
functionality still. Now, why can't something like that on the ground be used instead of waiting for something to be put in space?
Okay, so the basic question is we already have 8-meter telescopes on the ground. Why can't we use them? And maybe I should answer another question that that is inferred by that, which is, I'm sorry, why not do the visible experiment from the ground? We have perfectly good telescopes, and it's conceivable. I mean, there's a substantial debate among many of us about whether you can do this from the ground. It is possible to consider taking an 8 or 10-meter diameter telescope and correcting the wavefront. The wavefront that comes into this telescope gets distorted by the air, and it changes about every 100th of a second. It gets distorted by a huge amount. And this causes the star not to look like a tiny little tight star, but this big blurry thing that you see in photographs. That completely covers the planet, not even thinking about diffraction from the stars, just scattering from the bending of light waves through the atmosphere. And so in order to make a ground-based telescope work like one of these coronagraphs, you would have to have a deformable mirror out there running at about 1,000 cycles per second and almost perfectly measuring what the wavefront is and then correcting it quickly before it changes again. And it is conceivable that you could do this, but it's an extremely difficult experiment, and it sounds like it has all sorts of potential for failing.
Yeah.
Okay, just out of curiosity, do you have any personal preference between like a chronograph?
Yes, I have a personal preference. I mean, I'm trying to be even-handed about this, but I do think that the visible coronagraph is a much better system for the reasons that I said. You can see chlorophyll and you can see oxygen. And it's also a simpler system to build. It just sounds hard.
Yeah.
In range of speculation about deformable mirrors, why does the mirror have to deform? Why not the signal why not correct the signal that's coming off? That's what the signal.
Okay, so the question was, why do you need a deformable mirror on a telescope? Why not just correct the signal after you measure it? What happens, what I didn't show here is that as the light comes into a telescope, you have a nice flat plane wave, and it focuses down to a point which produces diffraction rings or whatever around it. All of that light, every little piece of that wave front interferes with every other little piece and produces the final image that you see at the back end, the diffraction pattern or the speckles, which are little images of stars scattered around that central image. It's not possible, I don't know how, to go backwards. After you measure the scattered light, if you have a bad image, I don't know how to go back and undo that. There are ways that you can remove the speckle by guessing what it is and calculating what the wavefront is, but then you've added so much noise to the system that it's really, it drowns out the planet image that you'd be looking for. Don't forget, this planet is 1 billion times fainter than the star, and you don't want stuff floating around in the focal plane.
Doctor, it seems there's room for a lot of improvement and development in visualizing outer space and tangibilizing, measuring things. Let's come at it from the point of view of noise, intelligent noise. Is there room for much improvement beyond what we're presently doing to see if we can pick up intelligent noise, or have we gone about as far as we can go?
Oh, you're referring to one of those lines in my first graphs that said, we can detect other civilizations by looking at their radio signals or something like that?
Intelligent noise.
There are people here at Harvard and at least one other place looking for laser signals coming from these stars. It turns out that, as you may know, if you build a really bright laser on Earth and shine it up into the sky, it can outshine the sun for a very small period of time, a microsecond or something. And if somebody else is sitting out there looking for these laser pulses and they put a filter on their telescope that only looks at helium-neon wavelengths, like so, then you can easily see a few photons from the laser, and there could be more photons from the laser than from the star. And it would be a great way of, you start a Morse code thing and you've got dot, dot, and you're sending a signal. If there was somebody out there doing it, it would be a great way of communicating. And people are looking for it. Paul Horowitz is running the 61-inch telescope almost every single night in the town of Harvard to look for these things as an auxiliary experiment. Whenever this telescope looks at another star, his experiment on the side sits there and measures whether or not there are laser photons coming from it. There is a parallel experiment, just in case you see things that are accidents. There's a parallel experiment going on at the same time somewhere down in Maryland near Greenbelt, looking at the same star at the same time to see if you see flashes at one telescope, you want to see them at another telescope to make sure it wasn't a mistake. And so people are trying. But nobody's found anything, or they would have been up here tonight instead of me.
Let's just take a couple more questions, and there's one way back there.
Yes, if life gets started, what do evolutionary biologists tell you likelihood of life evolving to produce chlorophyll and hence a lot of oxygen?
I don't know if anybody knows what the question was. What do biologists say about the likelihood of, I guess, basically life developing in the first place and then evolving up to produce plants and animals and us, right? I don't know. We only have one experiment, and my personal opinion, I'm not a biologist, so my opinion is not worth anything on that topic. But when you look around and you listen to people talking about how the same kinds of animal functions, eyes, arms, hair, feathers, have developed in many, many, many different species at different times in different places completely independently, it seems like there is a strong imperative, to my mind at least, for biological systems to develop higher and higher levels of complexity. And so I'm pretty optimistic. I mean, that makes me optimistic to think that if you're going out and looking for planets, that you might find life on one of them somewhere. There is another argument which goes back and says, well, if there is life out there, we would have heard about it. If there are people out there, they would be here by now. This is the alien, I guess, thought. And it's a respectable hypothesis. If there were people out there and if there were intelligent civilizations, they would have been there a long time before now. I mean, we've only been able to put out radio signals for 100 years or so. And chances are that they would have been doing it for the last 10,000 or a million years. Why haven't we seen their radio signals? I don't know. Maybe they're smart enough not to send out their radio signals. It's a really wonderful question. It's called the Fermi paradox, and I don't know the answer to it.
One more question, real quick.
In your talk, in your experiment, you use 8 meters for the size of the mirror.
Yes.
Why is 8 meters? Where is the calculation?
Yeah, good question, because I didn't talk about that.
And why is not 20 meters, or why not 1 meter, or even less than that?
Okay. All right. The reason is the question is why did I say an 8-meter telescope? Why didn't I say 20 meters or 1 meter or whatever? The reason is that if you look at the nearby stars and you measure you know what the distances to them are, okay, and you say that suppose that there was an Earth sitting at 1 astronomical unit away from that star, you now know what the angle. You now know. They used to have hooks that pulled people off the stage.
No, I don't have any idea.
Just this one answer. If you know how far away the planet is from the star, because you want to have liquid water on the surface of the planet, so it can't be too far, it'll freeze, it can't be too close, it'll boil off. You don't want it to be farther than Mars, for example. You don't want it to be closer than Venus, because those are two extreme bad examples. You want it to be like where Earth is or a little bit farther out. So you know what that distance is. You know how far away the star is. It's 10 parsecs or something away. So you can figure out what the angle is to that planet compared to the star. The angle is important because now when you build a telescope, you have a diffraction limit. The telescope and the angle that you can resolve with a telescope is given by the ratio of the wavelength of light to the diameter of this telescope, lambda over d. And that tells you approximately how tight a spot, an image you can make of the star and isolate it from another tight spot, which is the planet, which is what we're trying to do here. So you want that, you know what the wavelength is because we're talking about visible wavelengths of light. And so all you have to do is to take this angle and the wavelength and calculate what the diameter of the telescope is that makes it possible to do this. And the diameter turns out to be something like 8 meters. In order to have that Earth be at least 4 times that distance approximately away from the center. So that's where the 8 meters comes from. It also helps. It's not crucial, but it helps in collecting photons because the photon rate from that planet, the planet is very faint. And so the planet photons only come in at about 1 photon per square meter per second. And so you're collecting very few photons from this planet. So having an extra area helps. But the real crucial thing is the angular diameter of the system. And so that's why it's 8 meters. Now, you can have a little corollary to that and say, well, suppose I didn't really care about Earth. I just wanted to look for Jupiters, which is something that we're working on right now. because you want to start doing something simple. And so if you want to look for Jupiter's, Jupiter's 5 times farther away. So you can make a telescope that's 5 times smaller, and you can still succeed in looking for Jupiter's using that same ratio of numbers. And so if you make something like a 1 or 2 meter diameter telescope, then you can go out and look for Jupiter's, and that's something that we actually hope to do in the near future to practice all of these techniques. Okay.
Thank you very much, Dr. Traub.